Today is lecture 4 about more optimization for linear regression. So again, where we are, every time we're going to show this, we're still in regression. And the nutshell, the mental representation. So we covered about the task, the representation, and the scoring function, and also properties of the scoring function in the last week's lecture. And we also covered how to optimize that scoring function because it's a quadratic function. You can easily just set its gradient equal to 0 to get a closed form solution. That solution, the solution we normally call that normal equation-based solution. And today we're going to cover more how to solve it through other type of optimization method. And in last week, by the end, we also covered a little bit about computational cost of the normal equation-based solution. And we explained why, rather than doing kind of for loop, because all the computations here are mostly just about a scalar product, and then doing a for, and just across many examples, across many features. And rather than represent them as a lot of for loops, many hierarchy of for loops to calculate summation, calculate differences, we represent them as vectors or matrices. And there's a fundamental reason it's because we want to make use of the library. The fundamental library is those numerical optimization libraries, mostly using a full standard called BLAST standard. NumPy, in the end, the NumPy library from Python is really just a wrapper on top of those fundamental C version or C++ version of the library. And there are a lot of tricks using those libraries to make use of the computer architectures, especially CPU synced, vectorization structure, and memory hierarchy are highly considered. So to speed up a computation of vector-vector linear product computation or matrix linear solutions. So we have a few slides there just to review. There are generation 3, more generation of blocks, and try to read those. So they're totally extra, but if you're a CS purely trained computer science students, and read those descriptions can tell you a lot about why this type of formulation, how do this type of formulation connects to what you have learned from computer architecture, from operating system, from maybe other like software engineering. So it's closely related, and there's a reason why we do so in the end. So it's about speed, low time cost, and low memory cost. All right, so now let's come back to very mathy, not necessarily related to like, it's not about very computer science, but this is the core of machine learning. We really borrowed from the optimization, from the math, from mathematics, from statistics. And there's also a reason, we already have a normal equation solution, right? And it's closed form. So why do you go to other solutions? And again, there's reasons behind about theorems, about a stable solution. There's also about scalable computation. So whenever we learn, there are two factors we need to consider, is this mathematical properties and also computational properties. Most of the solutions here, there are reasons from both. Okay, so now let's go on. So in your homework one, we require you to implement 4 ways of doing performance fitting, or we call that performance training, of optimizing the loss function of least square linear regression. And the first solution is a normal equation. very easy, just one equation, you can get the solution, one step. And the other is something called gradient descent, and its extension, stochastic gradient descent, and mini batch stochastic gradient descent, which is the focus of today's lesson. And also the normal equation has close relationship to something even more actually faster from the optimization perspective called Newton's method. So we're not going to cover that. This is totally extra. Feel free to read those. Essentially, normal equation is just one step of Newton approach. All right, so let's come to a little bit more general. So we talk about in the nutshell, so whatever task and you want to formulate it as some kind of scoring function. And in our linear regression case, it's sum of squared error, which is the FF prediction on each samples versus the true prediction Y. And then you accumulate that differences of yi versus fi, take a square quadratic function, and then sum over all the training samples. And that is our objective functions. Through this objective function, we look for the best parameter in our linear representation. And this is the j theta. So just kind of to review, and our j theta, so it's a little bit confusing, like we used to have our representation is fx equals to theta. We used to use theta transpose x, right? And then somehow this changes to j theta. There's no x, there's no y anymore. So I hope you understand this part, because the fx equals to theta transpose x is the representation of the classifier, the regression in this case, the model we are learning. Fx is the model, it's the software program, like we emphasize. We use x1 pair to learn f, but how do you learn it? So this is more like a review of what we had before. So we use xy pair, trying to learn f, and that f is represented as theta transpose xi. And then here, when you have the x1 pair, the only thing unknown is theta. So j theta, it's really just the mechanism that helps us to figure out who is that program. What's the unknown part of that program? Program or model, in the setting, we just use them interchangeability. So, and from here, j theta is a measure. J theta measures how the loss between the true yi and fxi. And in our setting, our loss function is summation over all the samples, yi minus theta transposition xi quadratic. And in this form, in this formulation, you know xi, you know yi. The only thing you know is theta, and this capture the error. You want the error to be small. So this is our objective function, or loss function, or cost function. They mean the same thing. Again, so this is what we covered in the last week. Questions about this? Okay, because you already reviewed the lectures, hopefully. So, in the previous semester, I have to do a review again. So I hope this semester the quizzes really forces you to read the lectures and you understand all those very deeply. Okay, so this is our starting point, j theta, and the only parameter in the j theta, because xi, yi are given in the training data, the only thing not given is theta, and we want it to be small, so that's how we look for theta, by minimizing j theta. We minimize j theta, and hopefully the best theta star gives me the smallest j theta. That's the j theta our training data gives us, informs us. Okay, so now let's go to even more generic setting. So this process in the end is optimization. In the generic optimization, what you have is objective function. So let's now still just whatever function we normally call them fx. So here, just to distinguish with our previous small f, I use capital F to represent the objective function. Again, its parameter, its variable, it's whatever, it's x, or it can be represented as theta, can be represented w, whoever is unknown in this objective function. And the constraint, there are a lot of constraints in the real world optimization problems. Let's just put our problem there into this generic framework. So in our setting, our objective function is j theta, our variable is theta, and the constraint is theta is a p-dimensional vector. So the goal of the optimization is to find the values of the variables that minimize or maximize the objective function while satisfying the constraints. So in our case, we want to minimize it. We want to look for the theta, minimize the j theta. So very clear. So how to solve the generic objective function? So we already showed you one solution before. So if this fx function is a very nice function, assuming normally people call that strong convex, have some kind of shape like a quadratic shape, like a bell shape. When you have this kind of bell shape, nice, there's only one global minimal there, you can just look for the point whose gradient is 0. Because that's such a nice function, right? So this type of function, like a bell-shaped function, quadratic function, the easiest, the unique optimal solution is the solution whose gradient equals to 0. And there's only one unique solution. For this type of good function, good objective function, you just use that prior, the trick. Take gradient, set it to 0, and you get it. And this gives you the global best solution. Because there's only one point has gradient 0. So then this really relates to what is gradient? What is gradient? So to review gradient, we have to understand what is derivative, right? So I hope you still remember what is derivative. Derivative is the instantaneous rate of change. And it's the ratio of the change at a specific position of the fx versus the x change. It's really through this equation, you must already did this in your calculus class. This is a one-dimensional case, right? You can use this to derive what is the derivative of one variable function It's very easy. I mean, x plus h take quadratic. It's really a small shift, right? So when you have a small shift in the x and the ratio of the fx differences versus x differences, and you can just do the calculation. It's actually very easy to do the calculation. Easily we can derive a quadratic function, in this case x quadratic minus 3, its gradient at each point is 2x. And you must already memorize a lot of equations about generic popular functions, derivative functions. And this, the quadratic function's gradient is 2x. So, in this case, who is the minimum point? The minimum point in this case, absolutely very easy to see. Which point makes gradient equal to 0? This point makes the gradient equal to 0. And that's clearly the minimum point. And at this point, so assuming at point 2, what is its gradient? A derivative, which I should say this 1D case derivative is 4. So, gradient has directions. 4 is onto right, right? Let's go right. And the intensity is this slope. The slope of that curve, the intensity is 4, the direction is positive, means to the right. So, and then let's look at minus 2. So minus 2, the gradient is what? Minus 4. Minus 4 means what? Going to the left. And its intensity is that slope. This is minus 4. So what it really gives you is a direction and an intensity. Its direction points to what? Gradient direction points to the direction function increases. Gradient is a vector, and it's a number in this case, right? Because it's 1D. 4 means goes to right. It's positive, goes to the right, function increases. And when on the left, it's minus, it's negative, going to, actually your left is going, your left is a minus, and this is the right, is the plus. It has two properties. One is the direction, the other is the intensity. The intensity tells you the slope. The bigger the slope, the larger the number, the more sharp the slope. And that positive or minus sign tells you the direction. So let's see the 2D case. To understand the multidimensional case, we need to explain something. So when you have multidimensional, so whenever there's an objective function, there are two different ways to visualize it. The first way, we call that surface map. So surface maps is really just this map. So in this case, there are two-dimensional inputs, and you have a y. Your objective function is illustrated as one coordinate in the surface map. In this case, it's really the bell shape, and the xy is the theta 1 and theta 2 is here, and j theta is the z actual y dimension in this figure. Because our j theta function is a quadratic function, right? So that's why it looks like a bell shape. But there's the other way people always show you, actually called contour map. In the contour map, you actually don't have the j theta. The value of the j theta of that objective function is represented as the colors. The darker the color, the larger of the value. What you really see is only this. So a lot of those lectures or papers, they only show you this the contour map. So you have to really clarify first, am I looking at a surface map, which the objective function is shown as one of the coordinates, or I'm looking at a surface map, actually contour map. The objective function is only shown as a color using the intensity to show the high or low. So again, here, gradient vector points to the direction of the greatest rate of increase of the objective function, and its magnitude is the slope of the surface graph in that direction. So let's see. On the surface map, what you actually see is so let's just use this point as a point. So gradient really tells me actually go up. So it's from this point, because I'm at this like a bow shape, and at the surroundings going up, but that's actually on the surface, right? But the true move in the gradient is, let's come back to this definition of gradient now. So gradient is what? Gradient is a definition of a vector of partial derivatives. It's a vector in the p-dimensional space. It's a vector in the p-dimensional space, right? Okay, let's come back. So it's a vector. So when you have a multidimensional input, gradient is a vector. Let's see here. What is gradient in the two arrows I showed there? What is gradient in this figure? Gradient is a vector, actually, even though here is a number, but actually it's in the one-dimensional case, it's a point, but actually it's not a point. It's a move. It's a move direction. So what is gradient in this figure? It's actually this. It's not this. So what I'm trying to show here is just to show the slope. But what the true move is, from 2, my gradient tells me to move on the right, not move on the up. That's actually the y changes, not the x changes. Gradient tells you how to move x in the end. Gradient tells you how to move x, right? And of course, it should be the same size of x. When your input is 1D, it's 1D. When your input is 2D, it is 2D vector. Essentially, and it's going to be very clear in the next few slides, but just keep in mind, gradient tells you how to move in the x space. So in this figure, actually gradient really tells you how to move in this contour map. So starting from this x, the gradient direction pointed to, if your x move to that direction, the function will increase. Question here? This is fundamentally important. If you understand this, and then the gradient descent is very easy to implement. All right. So so we covered gradient form. It's really just the function versus each parameters partial derivative, and then you put them as a vector because it's the size. It's the partial derivative versus all these x elements. That's why it's the same size as your x vector. It tells you how to move in the x space. And the slope is really just a product of how you move in the x space influence on the move on the y space. So, and then what is gradient descent? Like we already said, gradient points to the direction the function moves up, right? So for our question, we want to minimize the function. That's why we go what? We go the opposite direction of the gradient. That's exactly gradient descent. Just as simple as it really is like this. So understand gradient and then gradient descent. Gradient goes to the direction function increases because we minimize the function. That's why we go the opposite direction of gradient, and that's the best direction for that point. So this is called gradient descent. Why do you want to use gradient descent? Because it can be used to optimize any type of objective functions as long as those points you can get the gradient. You can do the calculation of the gradient. It's not like the other what we are allowed. So the first solution we require, it has to be a really nice function, and you know there's just global only one good solutions, and to just set and this requires your function to be really, really good. And in our case, let's actually review, our function indeed is really good. So the j theta function, we actually proved, right? J theta function, because it's Hessian, so second order gradient, the gradient of the gradient is this form. And this X transpose X form, something is called gram matrix. Gram matrix is always positive semi-definite. When a function's Hessian is positive semi-definite, actually even more, in this case, if X is full rank, you can guarantee the Hessian of our j theta function is positive definite. Positive definite means positive curvature, and it's strong convex. Our j theta function is actually guaranteed to be strong convex. And that's why you can just use it guaranteed. If you just take the gradient equal to 0, you've got global solutions. And j theta is a good function. So that's why this works. And this is the last part. We got skimmed through a little bit quick. So if you want to understand what is PSD, PD, there are a lot of extra lectures in the lecture 3. So I put in the end, after the main content of lecture 3, feel free to read those. Actually, the proof is actually pretty easy. How do you prove X transpose X is when X is full rank, it's a positive definite matrix. But why the PD give you this convex good solution, that needs a lot of knowledge from optimization, so we did not cover in that slide. So feel free to read optimization books to discuss how the positive definite properties of Hessian related to the objective function. Okay, so normal equation, there's a reason for normal equation because our j theta is a good, very good function. It's a very good objective function. So that's why this trick works. And of course, it requires the X to be a full rank matrix. And we're going to cover if X is not a full rank matrix, what should you do? And that's the lecture 6 about regularization trick. So we're going to cover it later, but in the most cases, X is a full rank matrix. And if you need to use in your in whatever real world data analysis, so especially in the cases you have more features than data samples, you really can't use this. And we actually covered it because if there are more features than the more samples, it's guaranteed this is not invertible and you can't use it. Okay, so this is like lecture 2 and lecture 3, and there's a reason we keep repeating. And now we know that's a good function, but still we want to use this good function to introduce the gradient descent, which works for much more general cases, much more complex cases. So, for example, you have functions like this really wild, there are multiple like optimals, and there's no way you use the trick this equal to 0 to get the best solution. There's also when into the high dimensional cases, there are also plateau type of shape, more like this. You have a very huge plateau, and those have all gradient equal to 0. There's no way you get good solutions there. Okay. Okay, so now let's go to gradient descent in the two-dimensional case. As I emphasized, gradient is a moved direction. Okay, just to a little bit detour. If you need to go to a restroom, always, do you mind to sit on the side? Yeah, and also like a little bit quiet. Just be mindful to your fellow classmate. Okay, thank you. Try to sit maybe on the side. Okay. All right. So the 2D case, I mean, again, you have this. So this is actually not a bell, like a bowl. I mean, this is really like a wave shape, right? So I'm just trying to show you. In the end, gradient. So for this point, its gradient is actually pointed to out, and fx moves up. So so if you do a reverse direction of the gradient, you go from xk minus 1 go to xk. And that's clearly will push the function to be smaller, just from the surface map. And you take steps proportional to the negative of the gradient of the function at a current point. So here, there are two things, right? First, the more important is the direction. Second is how large do you do the step? So keep that in mind. There's always two things to when you're trying to move. First is the direction. Second is how large is that hop. Similar, it's just trying to show you again the one step. This is the original point in the variable space. This is the new point in the variable space. Just keep in mind, this really is pushing the xk minus 1 with a minus direction of the gradient proportional to the gradient vector. But what is that functional for? It, I tried to explain all this, and then actually this is the functional form. So the true function you use is xk, so the next round. So for my current round, I'm moving the direction of the gradient, the negative gradient, minus the gradient times a alpha. Alpha is something called the learning rate. And if you think about it, really how much do I change? What is the direction and size I'm making on my xk minus 1 is controlled by both the size of the gradient, also size of alpha. So let's keep this equation in mind. Come back to just again, I want to emphasize surface map versus the contour map. So what do I mean gradient descent on the surface map? What do I mean gradient descent on the contour map? Gradient descent on the surface map in the end is still you moves in the x space, right? But your f actually changes in their surface space. So there are two curves I'm showing here. This curve showing the changes of x, this curve actually show you the changes of fx. Or in our case is j theta changes smaller and theta moves actually into the middle minimum point. And the contour map, because I can't show the color, but yeah, so it's the outside is more color, inside is less color, means this is high j theta region or fx region, this is low j theta fx region. A lot of papers normally show you this. It just in the end, it's the most critical is about x moves in the x space. That's about it. Okay, I hope this explains, emphasize again and again, and clarifies the changes of f versus the changes of x. One is the action, gradient descent action. Changes of fx is the result of how you changes the x. Okay, question about this. Okay. And I hope this is this explains to you about this bow shape or bow, because the middle is really low. And the contour is really those contour showing the same height on the bow. And this is exactly how the contour map are constructed. Yeah, contour map, surface map. And x changes in the x space. Yeah. So in our case, if there's only theta, your homework has theta 0, theta 1, or WNB. It really is a changing of both the theta 0 and theta 1. And so in the homework, we give you two x, and the first x is actually pseudo feature. They're all 1. And so if you do a true programming, after the regression programming, you're reading the data, you actually need to add a pseudo feature, just because we just want you to kind of simplify the data loading. We already add that pseudo feature in there. So first column is pseudo feature, second column is x, third column in there is y. So the homework is a simple one-dimensional one case of x to y with a pseudo feature. That makes you need to learn two parameters because the pseudo feature there. So maybe let me review this. So in that homework, or similar to what we showed before, we have 2 and 1. So this is 2. So this is my first point given, and this is my 1 and 2. Second points given. So we actually did that calculation. We tried to learn a line here. So wx plus b. That's the smallest example we did last time. So our j theta is jwb, right? jwb. There are actually just one x and y in that given example. Is x plus b minus the 2 quadratic. Oh, there's a w. There's a w here. Yeah. W is w plus b, 2w plus b minus 3 quadratic if there's only 2 points. And our given xy is 1, 2, and yeah, it's this 2 points. 1, 2, and 2, 3. And that's, concretely, this is our J theta. And there's only one feature, but there are two parameters to look for. I hope you still remember this concrete example we did. Okay, all right, so gradient descent is a first order approach, optimization method, and you try to minimize to find a local minima of a function using gradient descent that takes the step proportional to the negative of gradient of function at the current point. And yeah, we already covered this. Let's do a very concrete example how to do gradient descent. So this is our fx, and this is our derivative fx, or in multi-dimensional case is gradient is 2x, and then using gradient descent, how to look for the minimal point of this function. You use this gradient descent updating rules. It's xk equals to xk minus 1 minus alpha times the derivative of gradient of that point. Okay, so let's start. So assuming I do not know where to start, I just do a random guess. Give me a guess of starting points. I don't know which x optimize fx, and my fx function is x quadratic minus 3. Minus 2, sure. That's my x0. My x0 equals to minus 2. Then what is the gradient at that step? So let me maybe make a table just to make it easier. So xk minus 1, gradient of that xk minus 1, xk minus 2, right? So my starting point is minus 2. Then what is my gradient? We just did calculation. Minus 4, right? And then what is my xk? So actually here it's 0 to 1, right? What is my minus xk? It's minus 2, assuming my alpha equals to 0.1. Yeah. Minus 0.1 times minus 4, right? So what is this? Did I calculate correctly?
Yes.
Minus, it's plus 0.4, it's minus 1.6, right? Is this correct? Yeah, where is minus 1.6? It's roughly here. So in the end, I moved from here to here. Go on. Minus 1.6, take gradient. Minus 3.2 and minus 1.6 minus 0.1 times minus 3.2. What should be this number? Who has a calculator? It's minus 128, right? Okay, I'm at minus 128. A little bit again, right? Okay, you get the point. You really get the point, right? I start from minus 2. I move. Your direction is I move right. I go move right, and that right direction is how the function decreases. And what I meant, gradient means is the changes of your x. So that's why it has to be the same side of your x, right? So it's really about this. So I move on the left, actually in your case it's the right. I move to the right, and then by a proportional step size, influenced by both the gradient, the slope, intensity, and also the learning rate. Okay, now let's change to a different learning rate. Let's assume alpha equals to maybe 0.6. So again, start from -2. My gradient is still -4, right? So what is my next x? It's -2 minus 0.6 times -4 is 0.4. Where did I go? I start from -2. I actually jumped to here. So I did a few more. So in the end, yeah. So it's here. So you can also start from -3, and what you get. So I'm still showing that slope. Again, this is a surface map, right? This is a surface map. I'm showing this objective function as a coordinate. That type of arrow pointed down shows you the changes of y. And this arrow in the x dimension shows you the move of the x. That's the gradient. So x0 goes to x1, from -3 goes to -2.4, and y, actually starting from this point, moves down to this point. All right, so this is almost the same as we did before, and let's see. You can also go to the other right side, and if you have 0.1, it moves to 2.4. Okay, so next few slides I want to show learning rate matters, because we already did this. If you do 0.6, the y really changes very wildly across the optimal point. It's not just in one side of the optimal points anymore. It actually really kind of oscillating from the left of the optimal point to the right of the optimal point, and just kind of oscillating. So this is the big learning rate, the influence of big learning rate. Question about this. Again, surface map. The gradient is the x change. That big is the y change, or the j change, objective function change. Question? Sure? Good question. It's a hyperparameter, you need to set it. But there are a lot of tricks actually guide you to set learning rate. There are also a lot of tricks. You can have big learning rate in the beginning, and then it has a functional decreasing of the learning rate as you go closer and closer to the optimal point. There are many, many tricks to do that. Yeah. Question? Okay, sure. Go on. So second thing is starting points matter. So we already tried, right? The 2 and 3 are +2 or +3. Now let's try -0.6. If you have -2.6, this is still a big learning rate. You have -0.6, and then that's the 2x, and -0. Yeah, so this is the 2x part, is your learning rate, and then because the -0.6 and the minus of gradient, you got a positive. So what you get, this is the starting, and where's my x0? Yeah, I think I did a few calculations here. -0.6, and then we go to 0.12 here, and then you keep going. And if you change to a different learning rate, if your learning rate, assume it's crazily large, 1.5, if your learning rate is 1.5, your new point will be 1.2, which means you're going to move from here to here. So this is the x change, right? It's much easier to see the behavior of the y change is, so, sorry, I actually started my x0 from 3 here. x0 equals 3, x1 equals to minus 0.6. It's trying to continue this. Yeah. Let's go back here. So the first is minus 3. If your learning rate is 0.6. This is wrong. So x0 equals to 3, and your learning rate is 0.6, and then your x1 will be 0.6. We already calculated. Then from x1 you calculate x2. It really moves to here, after this number. So this is the x0 move to x1, x1 moves to x2. What I'm showing again is the y change, right? Even though the x change is here, but y change tells you how the function moves from up and down. So even though this is still oscillating, but in the bigger trend, it's still kind of minimizing the function. So this learning rate is actually still okay. So even though it's oscillating from the left of the optimum point to the right, from the right of the optimum point to the left of optimum point to the left of optimum point, and you keep oscillating a bit, but you still keep decreasing that objective function. So 0.6 is still fine for this problem. But if you move to 1.5, from here, you're going to get a point x1 not decreasing the function anymore, actually increases the function. If x1 goes to 1.2, it's actually worse than, is it the case? I think so, yeah. So if you do this 1.2, this is actually 2. It's actually x2, sorry. We have all the bad notations. I should do this. This is actually 2. So if you use 1.5 as the learning rate, it actually moves, not necessarily decrease the function, it actually increase the function. So it really just tries to tell you the bad learning rate, oscillating is a bad behavior. And at the same time, it's not this gradient descent, not necessarily always decrease your function. It will actually increase your function because this is just too bad. This learning rate is too big. It jumps totally to the other side. Question about this. I should just do a new thing. Now, instead I'll use my old slides. Yeah. Is this confusing? Sure.
What if the learning rate is too small and it's trapped in the local minimum?
I mean trapped?
Yeah, in the local minimum instead.
Yeah. So I don't think gradient descent can solve this. It's just by nature. So there's a slide. Yeah, so actually let me clarify this page. I think it's when you have x1 equals to -1, your x2 will be 1.2, right? Who can help me calculate this quickly? If your x0 is 1.2, it's 1.2, it actually goes up. Yeah, it indeed goes up.
I think x1 is 6.
x1 6.
If x0 is 3 and alpha
X0
is
is
0.5.
It actually all starts from a -0.6, right? Okay. Yeah. Sorry, I must miss. Okay, I thought we use this to be easier, but okay. So in this case, yeah. So then you come back to the learning rate 0.1. Again, this is good behavior. -0.6 give you -0.48. You're still on the left side of this oscillation curve. So So the last thing what I want to tell you is objective function matters. It's related to the question you ask. Let's see. I'm optimizing, assuming the first function is x quadratic. My second function is actually 2x quadratic. Even the same starting point, the same learning rate, it really has different behaviors. So for example, in this case, I always start from x0 equals to 3, learning rate is 0.1. So if I'm on the green curve, it will gives me push to 2.4. So we already calculated the quadratic, this gradient is 2x, right? If you are on the purple curve, the gradient is 4x. It really pushes a lot more, right? So that moves your x0 go to x1, it's actually much faster. So even though you use the same starting point, same learning rate, just because the function itself is much more steep, it goes much faster. So this really tells you what? So there's no fixed starting point work in general very, very well for everything. There's no fixed learning rate, works very well for everything. You have to consider the function properties of your objective function too. Questions? So this is already a good case. Bell shape of function, just one minimal, and the behavior is very guaranteed. So you have to consider that 3 points in mind. Learning rate matters, starting point matters, objective function matters. And this is actually the summary I did. I just want to save time, so I did not do every one of this. So in the end, when you have, there are a lot of strategies to do control the alpha. You make alpha small. It's one strategy. And, but it may be bad. If your alpha is too small, you might not converge with many, many iterations. The other strategy is you start with big learning rate, you gradually decrease it. So as t increases, your learning rate decreases. But there's no uniform solutions. It matters to, it's about the properties of your functions, and this is a hyperparameter to tune. Yeah, that's the summary. Needs people prior, needs the designers prior, a good learning rate. But just luckily, the state of the art, the learning packages, their optimization package has done a lot of tricks and has good behavior in general. And so far, currently, the learning rate, they don't go too crazy. But when you implement your homework, keep this in mind. Actually keep all of this in mind. There's also, like I said, right, if your function has a very weird shape, there's one place is very steep, there's the other shape very plateau. It depends on the starting point. If you actually randomly start from the good side, it might convert really fast. If your starting point is the bad side, even though it's the same learning rate, it doesn't converge nicely at all. So that's also the function properties, right? But in general, like in the steep side, try to have smaller alpha because you don't want to have this oscillating behaviors in this kind of plateau place. It's very, very hard actually to have the gradient descent work well in the plateau type of cases. Question about this? All right, so just to follow up the question we just had, you might also have multiple minimal points. So far, I mean, the solution we can have is just multiple starting points. You try multiple random samples, and you just do that. Do the optimization by revising the starting point. Hopefully, that random action can pushes you out from the local minimal. Question about this? All right, so yeah, so then the gradient descent for linear regression, again, we just honestly, it's our j theta function. We derived this, and we'll give a reason why the matrix form 2. Again, review and the 4 formats. And this is the gradient vector. And gradient descent on the square linear regression is just to use the gradient descent function, and you get this. So this is our gradient descent updating rule, and you replace this delta into our gradient, and then put alpha, and that's it. And the theta is our parameter. The whole function is theta t plus 1 equals theta t plus alpha x transposition times y minus x theta t. That's it. This is how you're going to implement it in the batch version of gradient descent, because this uses all the training data. This is not stochastic. Stochastic is the next. This is gradient descent. Work on our j theta objective function. It's an iterative approach, right? So you start from random vector, random theta, and you iteratively using gradient descent, hopefully moves closer to the optimal theta. And they're actually theoretically guaranteed if your learning rate satisfies certain properties, the solution of gradient descent converge to the normal equation solutions. But that requires your learning rate satisfy certain properties. Question here? Yeah, it's really just use gradient descent. Okay, so in the figure, in the two-dimensional case, there's contour, so in the middle is the minimal. You really just moves from the random point, random starting point, closer and closer to the optimal point. In this case, we have optimal points. We know where is optimal point really is. So just to confirm, every time I like to do this size confirmation because it tells you a lot of things. So that gradient is, this is our P, n times P matrix training data, training matrix, because transposition give you P times n, right? The y vector is your training data, all the y represented as a vector. This is n times 1. This is x theta transposition, give you theta n times p times 1. This is n times 1. So if you think about this, this is actually y prediction. What is this number tells you is the residue, is the error from your current x theta t prediction versus your true y. And then times the accumulated weighted by the x. So the gradient actually has a meaning if you look at it very closely. And this size, this is the n times 1 vector, and this, because the minus operation gives you n times 1 vector, n times 1 times p times n gives you a p times 1 vector. That's exactly the vector in the x space. So in truth, every step when you're changing theta, you're moving within the theta space. Okay. So contour map. So if the learning rate is too small, you just spend a lot of time still very far, very far. If your learning rate is too small. But if your learning rate is too big, it's kind of oscillating across. It's from the left or right, really crossing the minimal point. So last, stochastic gradient descent. Okay, so very easy. So this is our gradient descent, right? And this gradient descent uses a vector form. And now we're doing, we convert the vector form to for loops. I know this is crazy. We convert the for loop type operation into vector form. Now we convert it back from vector form into for loop form. Yeah, so just keep that in mind. You can rewrite this gradient form into this for loop. Consider each gradient from each sample, which is actually very easy to do the calculation. It's really on the original form. I mean, it's here. So this is 2x, right? Something quadratic, you got a 2 here. And then you keep this. And that's the summation I from 1 to n x I theta t minus y I not quadratic anymore. And then you take a theta, so what's the next? I should write it there. I'm taking gradient directly on this for loop form now. Gradient versus theta. What's missing here? Yeah, xi. And this is the for loop based gradient form. Okay, so this is the vector, consider all the training samples. This is using a for loop, consider the gradient I calculated on each sample. So so rather than doing a gradient update, consider all the training samples, I only consider one sample. I'm only updating my gradient, consider that one sample. See here, this is a summation over all the samples. Now I just replace it by removing that summation. It uses just one sample. And this is called stochastic gradient descent. Very easy, right? It really just, rather than consider a summation of gradient vectors, considering all the training samples, only one sample at a time. This is stochastic gradient descent. And, oh, sure.
But in this case, you have to go through all the samples.
Good question, yeah. So you actually should, because this is not a true gradient, right? This is just an approximation of the gradient.
And so does every time you go through a sample, is that an epoch? Or
That's not an epoch.
Okay.
So what we meant epoch is you perform this gradient update the sample maybe 1, 2, 3, 4 until n. You cover all the sample already, that's one epoch.
Okay.
Yeah. And also remember very critically is because this order matters, right? The ordering of you use the first sample or second sample or third sample. You don't want to have a fixed order. You want to have enough randomness in the stochastic gradient descent, so you need to reshuffle your data. Because maybe that ordering, there's a lot of reasons why you want to do the shuffle. I can show you a paper, so I don't want to cover it here. It's a good practice, just remember that. It's a good practice to shuffle the data before performing stochastic gradient descent. All right, so yeah, so here I try to, because some people may be still confused about this vector form versus the sample form, and this is the derivation. How do you connect the two? So pretty easy. I'm not going to go over this, and you can just read it and to clarify. And then on the contour map, this is stochastic gradient descent. You can actually tell such a wiggle approximation, right? There's a lot of noise added in the gradient descent optimization path. And stochastic gradient descent actually doing something, it's called implicit regularization. And this is actually good. And I think I don't have time. Oh gosh. So I'm going to use your 5 minutes. I'm so sorry. And this is the password.